Okay, so today we are going to discuss section 13.3 and section 13.4. For the midterm exam, which we will have in 2 weeks, I will put the last homework paper before the midterm exam online today in the evening, and the material which will be covered by the midterm exam is equal to the material which was covered by the assignments, by the homework papers. So for the midterm exam, the material will be everything, including what I'm going to teach today. And if you find some, because if you look at our curriculum of this course here on the web page of Calculus, not on the web page which is related to this course. So on the general web page of Calculus, you will see that I have taught some of the sections which are actually not really part of the curriculum, or which are optional. But our midterm exam will also include those sections. So what I'm going to teach today about the curvature and about motion in space will be included as well in our midterm exam. But it's actually not really part of the curriculum of this course, or it's optional topics. Okay, so we are still talking about vector functions. So this here is a vector function. Normally we assume that the vector function is continuous, which means nothing else but the 3 component functions must be continuous. And we have seen already, okay, there is a one-to-one correspondence between vector functions, natural one-to-one correspondence between vector functions and space curves. Namely, you consider, you map this vector function onto the curve, which is traced out by the tips of the vectors given by this vector function. So, which you can interpret also as the graph of this vector function. And this gives you a natural one-to-one correspondence to space curves. So such vector functions, you can interpret it as a space curve. This is just the same as a function which we discussed last semester, function of one variable. You can identify it with the graph. Now, last time I showed you, okay, what the derivative of such a vector function is supposed to mean. Namely, we just take the same definition as we have seen last semester, but of course now interpret it slightly differently. So you look at this here. Okay, so actually you have here the scalar product, 1 over t minus t0, the scalar product with this vector here, because everything is a vector. But if you define the derivative, t0, if I define the derivative of a vector function at the point t0 like this here, we saw last time that this means that the vector function is differentiable if and only if all the component functions are differentiable in the usual sense we have discussed last semester. So everything just boils down to the theory we have discussed last semester, but for apply to those 3 functions here. So this was for the first derivative, and the reason why we defined here the first derivative is just the same as the reason we have defined the derivative last semester. Namely, last semester we defined the derivative because we used the derivative to define the tangent. Okay, so if we have defined the derivative, we can define what we mean by a tangent. And the same here. So here you have a space curve corresponding to this vector function. And the meaning of the derivative, or I should say it differently. We use, if the derivative exists, then we can define at a point which has here this position vector rt0, so which is the tip of this vector here. We can define the tangent in this point, or to this point. Namely, we will say, okay, the tangent is the line which passes through this point here, and the direction is given by this vector here. Okay, so that's then the definition of the tangent. So for this definition of the derivative, it's quite obvious why we do this. But of course, formally, you can also apply higher derivatives for vector functions. But we have to clarify then what is the meaning of the higher derivative, or why are we interested in the higher derivative? Okay, but formally we can define it. So we define okay, the second derivative is just the derivative of the first derivative. Okay, and we can go on like this. We can define the third derivative and so on. We will discuss today more or less what is the meaning of the second derivative. Okay, this will be one of the topics we are going to discuss today. And apart from the derivative, from higher derivatives, you can also define integrals for vector functions. Now, how we are going to define, for instance, the integral from a to b of a vector function dt. Okay, so we can do the same as here. Okay, we just look at the definition we have seen last semester and check whether this definition makes sense. So last semester we defined this as a limit, then some h tends to 0, or we always call this delta t, and then we have a Riemann sum I from 1 to n. So we divide the interval from a to b into n subintervals. In every subinterval, we choose a sample point. Okay, and then what we do is we look at the sum. We multiply the sample point with the length of the I subinterval. Normally, what we choose for the subdivision of the interval AB is we will divide it into subintervals of the same length. So the length will then be delta t. Okay, and we look at this Riemann sum here, and we look at the limit, and if the limit exists, then this symbol here is defined via this limit here. Now, this definition you see makes also perfect sense here for vector functions. Okay, so you just have to interpret this is here the scalar product because this is a scalar here, this is a vector. But of course, you can look at this vector here. So this will give you. Sorry, I should write here n tends to infinity. But this is the same here. This will give you a sequence of vectors, and for a sequence of vectors, we have defined. Strictly speaking, we haven't defined what the limit is, but you can easily imagine what the limit is. You just define it component-wise. Okay, but we have defined the limit of a vector function r of t as t tends to t0. Here you have something similar. You have a sequence of vectors, and similar you define the limit just component-wise. So this is something which makes sense here. Okay, so you can say, okay, we define an integral for vector functions just in by using this limit. But of course, you have to ask yourself, okay, is this useful, this object? Okay, or why do you do this? It's like if last semester, when we look at the function, okay, we had the motivation in order to study the integral. The motivation was, okay, we wanted to compute the area below the function and above the x-axis. Okay, but here this is a vector. This is a vector function. Okay, so of course you have to. If you can define such an object, but it's not necessarily useful. Okay, and we will discuss later on why this is useful. I guess you have seen this already in physics. This is a very convenient notation. So here, the reason why we define this is more or less because it's a convenient notation, which allows us, for instance, in physics, to talk about certain things more easily because we have this convenient notation here. But you see that if you write everything out, okay, so if you introduce coordinates, component functions for the vectors, then of course, because of the definition of the limit, as I said, is just component-wise. Also, the definition of the sum is component-wise. Also, the definition of the scalar product is component-wise. So if you rewrite everything in terms of components, then what you get is, okay, in the first component, you have the limit n tends to infinity, and then the sum I from 1 to n, and then you have f of f ti. Maybe so here I choose just some of the endpoints, but in general I can choose any sample points times delta t. And then in the second component, just the same. t of ti star delta t, and then we have also a limit n tends to infinity, and then some I from 1 to n, and then h of t I star delta t. Okay, and this is the third component, and you see that the integral over a vector function exists if and only if the integrals over the 3 component functions exist, and you can compute the integral over a vector function just as the vector which is given by, in every component you have the integral over the component functions. This is what you see here from, this is what you get by using this definition here. So you just do everything component-wise, okay? Which means you have all the laws we have discussed last semester. In particular, you have also the fundamental theorem of calculus. So if this function here is continuous, okay, then you will have, then this function has an antiderivative. Okay, antiderivative you just define here in this context in the same way as we have defined it last semester. So if this function is continuous, you have an antiderivative. Okay, and the antiderivative is given by the integral from a, where you replace the upper limit by some variable, say x in this case. Okay, and you just define the antiderivative, okay, by doing this component-wise. Because if this function is continuous, this means that those 3 functions are continuous. So all those 3 functions by the fundamental theorem of calculus have an antiderivative, and you just write here the first antiderivative, the second, and the third, and you get the antiderivative of this one. Okay, so everything follows from last semester because it's just defined component-wise. So you have again that if you have a continuous vector function, okay, then the continuous vector function has an antiderivative, and you can, this was the first part of the fundamental theorem of calculus, and you have the second part which tells you whenever you have whenever you find an antiderivative of this function here, you can use the antiderivative in order to compute this definite integral just by evaluating it at the upper limit minus the lower limit. Everything holds, okay? And I don't have to prove it. I get it for free because everything is defined here component-wise. Okay, so any questions to this? So we have also for vector functions higher derivatives and the integral. And of course, you can also you can define the indefinite integral where you don't have limits, which is just a short notation for the antiderivative. Again, motivated. The reason why we have discussed the indefinite integral, why we use this symbol for the indefinite integral last semester is again the fundamental theorem of calculus. Okay, so everything you can define also for vector functions. But as I said, the first derivative, okay, we understand. Okay, it makes sense because we can use it to define a tangent, okay, of this space curve. And the tangent, the reason why we are interested in tangents is always the same, because the tangent is much easier. It's a much easier curve than this curve here. So you can locally replace it by the tangent. But for higher derivatives of a vector function, okay, because everything defined component-wise, we are not clear how to. We haven't discussed yet. Okay, what is the meaning? Why are we interested in the second derivative, or why are we interested in the integral of a vector function? This is what I essentially want to do today. So I wanna give an answer to this question. For the integral, you should know it already from physics, because this kind of notation is convenient in physics. Okay, and you can just look at it as a kind of notation which is convenient to write things shortly in physics. Okay, this is something you should already have seen in other classes. Now, the first thing I want to discuss is what is the meaning of the second, or I want to give the second derivative some meaning. Okay, now, if you think back last semester, we also defined the second derivative, and the second derivative was a kind of measure. So in some sense, it will measure. It will say something about how curved the curve is. Okay, in which direction? Because we saw if the second derivative sign is positive or negative, we saw that we either have concave upward or concave downward. Okay, so it says something about the way the tangent is changing. Okay. Now for the second derivative, you will here for a vector function you will expect something similar. In particular, in the next chapter, next section we want to discuss. Okay. Okay. You see here you have a space curve. Okay. And you see that maybe you will say that at this point which I draw here, okay, the space curve is not very curved. Okay. But here the curve is very curved. Okay. Curved with curved I mean, okay, is it like if you go something like this, I'm not going on a curved line, okay, but if I'm going like this, okay, I'm going on a very curved line, okay. So I want to introduce a measure, okay, which helps me to measure how curved the curve is, okay, and this measure will be called the curvature. Before we discuss the curvature, we have to once more recall the arc length. Now we defined the arc length for a plane curve last semester. So first the arc length. Okay, so last semester we talked about parametric curves, but in the plane. So you can say plane curves. Okay. So if we have a plane curve, and if we assume, so the t goes from A to B, and assume that the derivatives are continuous, okay, so we saw last time that, okay, then, so you can think about this parametric equations here as some plane curve, some curve in the plane. And last semester we discussed the problem of computing the length of the curve, and we obtained the formula. So L is equal to the integral from A to B, and then you have the square root of you take the derivative of f with respect to the parameter squared, plus you take the derivative of g with respect to the parameter squared dt. So this was the so-called arc length formula last semester. Maybe I should say that the curve is only traced once as t goes from A to B. So for instance, if you look at the circle, of course, if you just look at the circle, this plane curve is different from this one because this one has also a direction. And here you can also, depending on the range of the parameter, you can run around the circle twice. Okay, but for this circle, for this formula to hold, okay, we should traverse the plane curve only once as t goes from A to B. Now, this is the formula we proved last semester, and you can just use the same proof to prove that the arc length of a space curve is computed by the same formula. You just add the third component function. So now we have a space curve. Again, for t, we go from A to B. And again, we assume that the derivatives are all continuous. Okay, then you can easily prove the same formula from A to B, the square root. Then the derivative of f with respect to t squared plus the derivative of g with respect to t squared plus the derivative of h with respect to t squared dt. Okay, and we can write this now more convenient, namely, so this is the space curve, and if I denote the corresponding vector function by r, then this is here just the length of the derivative of r. Okay, because the derivative here was defined component-wise, and if you compute the length, you just get this here. So we can write this now more convenient. So for the arc length of a space curve, we have this formula here. Now, something which I have mentioned last semester and which I want to recall is that actually, if you use different parameterization, if you have such parametric equations, okay, you will get a space curve. In this case, a plane curve. Okay, but of course, you can also use a different parameterization for the same space curve. Okay, and of course, this formula is independent of the parameterization you choose. Okay, this should be quite clear. Okay, because if you change the parameterization here, okay, what you get by this formula shouldn't be different. So this formula is independent of the parameterization you choose. Normally, for one given plane curve or space curve, you have many different ways to parameterize it. Okay, so for instance, if you look at the circle, okay, one possible parameterization is okay, for x you choose cosine of t, for y you choose sine of t, and t goes from 0 to 2 pi. This is for the unit circle. Okay, but another one is x is equal to sine of t, y is equal to cosine of t. Also works. Okay, you just run around. You start somewhere different and run around different. Okay, so for one given plane curve, there are many different parameterizations which you can choose. But of course, this formula will always give you the same value. Okay, because the arc length should be something which is independent of the parameterization. Now, so for the arc length, this is quite clear. But for the properties we will discuss later on, for instance, if you look at the second derivative, okay, then the second derivative or the first derivative, okay, is something which of course depends on the parameterization. Okay, if you give a different parameterization, it seems to look different. Okay, so as I said, what I wanna do is I wanna measure the how curved the curve is, and roughly speaking, from last semester we know that okay, the second derivative should express this. Okay, so we take just the absolute value of the second derivative. But if we take if we take the absolute value of the second derivative, this depends on the parameterization. Okay, but how curved the curve is shouldn't depend on the parameterization. Okay, so keep this in mind. Now, something which we have discussed last semester as well is the so-called arc length function. Okay, so the only thing you do is the upper limit here becomes a variable, and then what you get here is a function. So this is what we call the arc length function. Actually, we should interpret this as let's write this as t, just to make this. This makes this awkward here, but let's write here s. Just to make the notation consistent to what I want to say next. Yeah, this is what I want to do. Okay, so you see that the derivative of the arc length function with respect to t. For this, you get something very easy. This is just by the fundamental theorem of calculus. This is just the length of the derivative of the vector function. Okay. Now, what I want to do is sometimes, okay, it's possible if you have the arc length function. Okay, sometimes it's possible to find the inverse function of the arc length function. Okay, and now in many cases. So we have given a vector function. Okay, t is our parameter. Okay. Now I told you already that okay. So this very much depends on the parameterization. Okay. So we want to introduce a special parameterization. Now this means we want to introduce a special parameter t. Okay. Now the parameter which is very good choice is the arc length. So we parameterize the space curve with respect to the arc length. This means that the parameter has the meaning of the arc length. Okay. So for this, you need that you can solve this, that you can find the inverse, then you should plug it in, and you find what is the range for S. Okay. And then you can reparameterize the original function, the original space curve with respect to the arc length. Okay. So for instance, I give you first an example, and then we discuss why is this useful. Okay. So for instance, if you look at the helix. So the helix is given by this vector function cosine of t times I plus sine of t times j plus t times k. So this is what we call the helix. This will be always our running example today. Okay, so you see that if we want to compute the arc length here, so what we have to compute is the derivative. So the derivative is minus sine t I plus cosine t j plus k. Okay, so you see that the length of the derivative is getting very simple because sine square plus cosine square is equal to 1. So what you have is square root of 2. Okay, so you see that the arc length function, if we start with the parameter t from 0 to t, okay, of the helix, so here I should write s, is an easy function, this one. Okay, so you see that t is equal to s over square root of 2. Okay, so I can reparameterize the helix, okay, by introducing the arc length as a parameter. Okay. So if I reparameterize it, okay, the only thing I do is I replace t by okay. So this will also give you the helix, okay, but the parameter s, the meaning of the parameter s is different. Okay. Now, maybe already from here you can see what is the advantage of introducing the arc length as a parameter. If you okay, so let's say this is a space curve, and let's say normally for the arc length, okay, we have to say, okay, where do we start to measure? Okay. So for the arc length function, you see that here I started at 0 with the parameter 0. So normally, in terms of this space curve, okay, I will start at some point. So for instance, here. Okay, so from here I will start to measure. So let's say this corresponds to t is equal to a. Okay, so the point from which we compute the arc length. Now, if I introduce the arc length as a new parameter, okay, then, for instance, if I want to compute now with the new parameter, I want to compute, okay, what is the point given? So I have here r of s, and for instance, what is the point which corresponds to the tip of, let's say, r of 1? What is the meaning of this? This means, okay, because the parameter has the meaning of the arc length. Okay, so I have to go from here, okay, away. If I'm standing on the curve, okay, and walking, okay, I have to measure 1 meter. I have to walk 1 meter, and this point is then given by this one. Okay, so if I reparameterize the original curve, okay, by the arc length, okay, then the meaning of the parameter becomes, okay, if you have to plug in 5, you have to walk on the curve starting from here 5 meters, okay, and then this is the point. And now you see what is the advantage. Maybe you realize already what is the advantage of introducing the arc length of parameter, the arc length as a parameter. If I use this parameterization of the curve, because I'm just walking on the curve, okay, so this parameterization is kind of independent from the coordinate system. No matter where the coordinate system is, okay, I'm walking on the curve, okay, and this will be the right parameterization of the curve in order to define the curvature, because this is the parameterization where I'm walking on the curve, okay, And I do not care what is the coordinate system. Now, this is something which is done very often. This is done, which is done very often here. Namely, we very often, for a given space curve, we very often introduce the arc length as a parameter. Okay. Once more, the reason why we do so is because the parameterization then becomes independent of the coordinate system. Independent in the sense that you are walking on the curve. Okay. Now you might say that in this example I was lucky. Okay, I could compute the inverse of the arc length. Okay, but if I give you a very complicated vector function here, okay, this integral might become very complicated. The expression might become very complicated. It's maybe even not possible to solve it, or if it is possible to solve the integral, no chance that I can compute the inverse. Okay, then, but still in most cases we say, okay, we introduce, we say, okay, it's possible to introduce the parameterization as parameterization, the arc length as parameter. So we will do it without doing it. Okay, so our results then, we will first define things. Okay, for the curve where the parameter is the arc length. Okay, and then the first thing which we always have to do is, okay, to figure out if we do not have this parameterization where the parameter has the meaning of the arc length, okay, how can we rewrite the definition such that we can compute the parameter which we have introduced for any given parameterization of a space curve. You will see in a minute what I mean by this. Okay. So the main thing is you do not have really, if I say in the sequel, okay, we will look at the vector function which is parameterized by the arc length, and if you worry, okay, how should, in some cases this is not possible, okay, this is not important, okay, because for the results which we then see, okay, you can most of the time you can always start from this curve in order to compute the parameter, but we have to rewrite the definition suitable that we are able to do this. Okay, any questions so far? So the main thing you should understand here is that introducing the arc length as a parameter is a very good thing to do. This parameterization is very special and it is very good because it is independent of the coordinate system. Okay, so now let's say we have given a smooth space curve or vector function. Okay, then what we can define is smooth once more means that the derivative is never equal to 0. Okay, so we can define the unit tangent vector, which is defined as okay, I look at the derivative and normalize it. Okay, so this in particular I'm not going to divide by 0 if the vector function is assumed to be smooth. Okay, so this is the unit. This is what I called last time the unit tangent vector. Okay, so once more, if you look at some space curve, okay, you look at for instance at this point, okay, we have a unit tangent vector. Okay, now if the curve, the curve I'm talking about is always a space curve, okay? It's not a plane curve. So if the curve is in this point very curved, okay? You understand what I mean by very curved, okay? If the curve in this point is very curved, okay, then the unit vector, okay, will change very quickly. The direction of the unit vector will change very quickly. If the curve in a point is not very curved, then the direction of the unit vector will not change very quickly. So it's kind of, you have to look at the change of the unit vector, which tells you have to look at the derivative here. Okay. So a measure for how curved the curve is at some point would be the derivative of the unit vector and the absolute value of it. Okay. But this kind of measure is not very good because it depends on the coordinate system. But the curvature should not depend. Should just depend on the properties of the curve on the curve, not on the parameterization. Okay, so we are first introducing the arc length as a parameter. We use this kind of parameterization, and then we take the derivative with respect not to t, but to with respect to s. Okay, and take the absolute value, and this number you get is called the curvature. Okay, so this allows us to define the curvature. Okay, so the curvature, this is the standard symbol for the curvature kappa, is defined as the length of the derivative of the unit vector. But here, so the unit vector is parameterized with respect to the arc length with respect to s. Okay, and this here should be a measure, a good measure, okay, which helps us to measure in a given point, okay, how curved is the curve there. Okay, so roughly speaking, okay, if you forget about what I said, okay, roughly speaking, if you just look at this definition, it's the second derivative, because this is the first derivative, and you have one smaller derivative, so it's the second derivative which you look at. Okay, but what you have to worry about is that if you just take the second derivative, okay, and the absolute value of it, this is dependent on the parameterization. So we have to introduce, we have to pick out a special parameterization which is independent of the coordinate system, which you get if you introduce the arc length as a parameter, and then you look at this here, and this is the curvature. But of course, it's not very convenient, as I told you before, that you require here that the original curve is that the parameter of the original vector function is the arc length, but this doesn't matter because of the chain rule. You see that this is equal to, using the chain rule. Okay, so now you have everything with respect to t. Okay, not the parameter. Sorry, not the arc length as parameter anymore. So what you get here is okay. So this is just the derivative of the. This is a very awkward symbol which I use here, but so this is not pi here. Okay, this is t, but a vector. So this is this here, and here we have ds over dt, but ds over dt, we just saw that this is the length of the derivative. Okay, and you see that this formula here, you get the same. Okay, but this formula does not depend on s, so you do not really have to parameterize first the given space curve with respect to the arc length. Okay, you can just use this formula, and this formula will be independent of the parameterization because it's equal to this one. Okay, so this is the curvature. Now, maybe let's look at one example to check whether this really measures how curved the curve is. Actually, what I have told you so far is apart from space curves, you can also apply it for plane curves, okay? Because this definition, okay, also works for plane curves. Okay, so let's maybe look at the circle. Let's say with radius a. Okay, so this is the parameterization of the circle. Now, okay, so what do we have to compute? We have to compute the derivative, which is minus a times sine ti plus a times cosine of tj. Then we have to compute this here. So we have to compute the unit tangent vector. First the length. So you see that the length is just equal to a. Okay, so we have to divide this here by the length. So we see that the unit tangent vector is equal to minus sine ti plus cosine tj. Okay, and we have to take the derivative here. So the derivative is minus the cosine of ti minus the sine of tj. But we just need the length here. So you see that kappa is equal to the length here of this one, which is 1. Okay, so 1 over this one, a. Okay, of course this makes perfect sense. Okay, because you see, if you have a circle, okay, if the radius of the circle is very, very large, okay, then if you walk on the circle, you walk something like this here, you will not feel that the circle is curved, okay. If the radius is very large, okay, it will feel it. If you are in a certain point and you just walk a little bit, okay, you cannot differentiate between walking on a line and walking on a circle, okay. But if I give you a very, very small radius, so you have to walk like this, okay, then you will feel that the circle is very curved. So if the radius is getting smaller and smaller, the curvature is getting larger and larger. Okay, so this makes sense. So here for this example, we see that the curvature really measures what it is supposed to measure. You see that like this here, using this formula, of course, you can compute the curvature, but it would be nicer to have a formula which expresses the curvature just in terms of derivatives of the given vector function, because then you just have to plug in and to compute the value. Now, indeed, there is such a formula, namely, I'm not going to prove this because the proof is trivial, just doing the computations. Okay, so you can easily prove that this formula here holds, which expresses the which tells you how to compute the curvature for a which expresses the curvature, in terms of the derivatives of the given vector function. So here you just have to plug in, okay, in order to compute the curvature. Now, for my students from last semester, you might remember this sounds a little bit familiar. I hope so. Okay, because last semester I introduced this already, but different. Okay, so last semester I discussed one of the exercises in our textbook when I talked about parametric curves, where I was also introducing the curvature. Now, how did I define it last semester? So if you have a plane curve, because last semester we discussed plane curves. I defined the curvature at a point. Okay, I looked at this angle here, theta, and I defined the curvature, okay, as the rate of change of this angle with respect to the parameter, the absolute value. Okay, so last semester I defined kappa as this here. And then I proved that if you have, this is one example in our textbook. If this is a parametrization of the curve, I showed that in physics or in applied sciences, it's very often the usual notation that if I take the derivative with respect to the parameter, I just denote this by x and the point above the x. So this means taking the derivative with respect to t. Now, starting from this definition, I showed you last semester that the curvature is given by x dot y double dot minus x double dot y dot over, and then x dot square plus y dot square to the 3/2. Okay, so I proved this last semester, starting from this relation here. Okay, and you easily see that this is the same as this as the expression you would get by this formula. Okay, why? Because our r of t, okay, this is a plane curve, but I can add the third coordinate. So our r of t is f of I just write it in terms of x, y, and t, but everything x, y, and z, but everything depends on the time. So here I have x, here I have y, and here I have 0. Okay, so you see that for the denominator, so this one would be you have to take the derivative here. So here you have x point, y point, and this is still 0. And the absolute value is the square root of x point square plus y point square to the cube. So you have already this here. And you see that for the cross product, okay, you have that because you are in the plane, so the cross product must have the direction in the z-axis. So the x coordinate and the y coordinate of the dot product is equal gross product, not dot product, of the gross product is equal to 0, and for the last coordinate, you exactly get this here. Okay, so this corresponds to what I have explained last semester. Okay, so also this here, also this definition is independent of the parametrization because it corresponds to the definition I gave today. Here, maybe it's not so obvious to see that this is independent of the coordinate system because here it seems to depend on the coordinate system. Okay, but in fact it's not. Okay, and of course I can also use this formula or this new definition of the curvature to figure out, okay, what is the curvature of a graph of a function as discussed last semester. So if I have a usual function like this here, okay, I can interpret this as a vector function. So in the space, let's say the parameter is x. So I have in the x direction x, in the y direction f of x, and 0 in the j direction, in the k direction. So. Okay, and if you look at this formula, okay, so what do we get? So for the first derivative, as a vector function, what we have is with respect to x, of course, now is I. Then here we have the usual first derivative, j. This is 0, and for the second derivative, okay, so what we have is only this is left. So if I compute this here, what do I get? You see the denominator is easy. The denominator is this one. So I have 1 plus the first derivative of x squared, okay, to the 3/2. And for the enumerator, okay, I have to multiply the cross product of this here with this one. Okay, but you see that for the cross product you have this. So if you have the cross product of this times this here, you can multiply this with this and multiply this with this. But the cross product of a vector with itself is equal to 0, and the cross product of I and j is equal to k. Okay, so what you get is here the absolute value of the second derivative. So you see that also this makes perfect sense because somehow the second derivative, okay, should be related to, should measure how curved the curve is. Okay, now the curve which we are looking at is the usual graph of a function. Okay, if you have a graph of a function and you wanna know in a point how curved is the curve there, okay, should depend on the second derivative. But the second derivative would again be dependent on the coordinate system, so you have to normalize it suitable. That's why you get something like this here. For instance, here this is a good point to explain once more why this special choice of the arc length as parameter is necessary. Because if you look at this function, also this example, maybe you remember or maybe not. I have discussed it last semester. So the graph of this function, of course, very easy. This one. If you look at this example, okay, you see that if you would define the curvature for this situation just as the second derivative, okay, then the curvature for this example would be constant, okay, for every point. But of course, if you look at the curve, okay, this is not true, okay, because if you are standing here, okay, the curve is certainly more curved than here, okay. So just the second derivative does not reflect how curved the curve is. Okay, but if I use this this formula which comes from our general definition, then you see that the curvature is equal to, so the second derivative is equal to 2 over, and I also have this here. So I have 1 plus, and the first derivative, which is 2x, so I have 4x squared to the 3/2. So you see that at x is equal to 0, okay, this kappa here, this function is achieves its maximum. Okay, at x is equal to 0 is equal to 2. here, and then we go something like this here. Oh, symmetric. And you see this, it's again, sorry. You see this again makes perfect sense, okay? Because here the curve is most curved. And as you walk up here, the curve is getting less and less curved. So the curvature should go to 0. Okay, so you see that this formula here is a much better measure for how curved the curve is than just taking the second derivative. Now, the next thing I want to discuss is the following. So, assume this is a given space curve. So, if you fix a point, then you have in this point, if you assume that the space curve is smooth, you will have the unit tangent vector at this point here. Now, of course, there are many, many vectors which are perpendicular to the unit tangent vector. So it's easy to find here a vector which is perpendicular to the unit tangent vector, and such a vector obviously not unique. Okay, but there is a special one, because last time we showed the following. We showed that if you have given a vector whose length is constant, and I should say, if you have given a vector function whose length is constant, and you compute the derivative of this vector function, then the derivative is orthogonal or perpendicular to the original vector function. Okay, so we know that this vector function here, okay, satisfies that the absolute value is equal to 1 by definition. Okay, so we know that from the result which I showed you last time, that the derivative of this vector function is orthogonal to the vector itself. Okay, so this is what I showed you last time. So you get one vector which is perpendicular to this vector, okay, by just taking the derivative. Okay, and because this vector does not necessarily have length 1, so we normalize it, and the normalized vector is called n. So n is the normalization of the derivative of the unit tangent vector. And this vector is called a normal vector. Because there are many normal vectors, sometimes you have to add principal normal vector, unit normal vector. Okay, so this is one vector which is normal, perpendicular, or perpendicular to this vector here. Okay, and we will see that this vector is very special. In this case, this vector would be like this here. And so this is our n. And once you have two vectors, you can consider the vector which is normal to both of them, which is given by the cross product, and this vector is called the binormal vector. Okay, so the vector which you get, so actually also n depends on t, everything depends on t actually. The vector which you get if you compute the cross product of those two, I'm not sure the order, of course, is important, so which one? The other way around. This vector is called the binormal vector. Now, normally, certain planes are defined together with a point of a space curve. First, the plane which is spanned, or which contains n and b. Okay, this plane is of course normal to the tangent vector, so this plane is called normal plane. So the so-called normal plane is the plane which contains n and b. And the point here, this one. But more interesting than the normal plane is the plane which contains p, the unit tangent vector and the unit normal vector. This plane is called the osculating plane. So the osculating plane contains. Actually, I shouldn't. But you know what I mean by this. I shouldn't say it like this because the vector should, the vector n and b can be, of course, removed from the plane because if I move the vector, it's the same. Okay, but you know what I mean. So the osculating plane contains the unit tangent vector, the unit normal vector, and b. Now you see also in our textbook it's explained. This word is coming from Greek, which is kissing. So you can call you can also call this plane kissing plane. Now why is the plane called like this? Because this is actually the plane. If you have this point here, okay, you might be interested in the plane. Which plane contains in some way the largest part? I'm not going to make this clear what this means, but you have a plane here. Okay, you have several choices for a plane which is going through P. Okay, you are interested in which plane contains the largest part of the curve. Okay, so of course if your curve is given like this here, a plane curve, okay, and you take the plane which is like this, or the normal plane, okay, this plane will not contain a lot from the curve, okay. But if you take the plane which is the blackboard, this plane will contain everything from the curve, okay. So you see, if you have a space curve, okay, not necessarily like this, a plane curve, but if you have a space curve and you have a point, you're normally interested in which plane contains the largest part of the space curve. And this is this one, the osculating plane. Okay, this can be proved, this can be made precise. We're not going to do this. But this is the meaning of the osculating plane. And then what we define normally is the so-called osculating circle. Now, so this is the third thing, the osculating circle. Okay, so how is the osculating circle defined? You find this in our textbook. I'm not going to write it on the blackboard. So the osculating circle lies in the osculating plane. Okay, then so for instance, if you look at this here, so it would lie in the plane which contains the largest part of the space curve, locally at the point P. Then this information is not enough. You have also to say on which side of the space curve. Okay, so the osculating circle is on the side of the space curve to which the normal vector points. So it will be here. Okay, then it shares the point P with the space curve, and it shares in the point P the same curvature. Okay, the curvature already determines the radius, because we know that if the curvature here is kappa, okay, in this point, then the radius of the osculating circle must be 1 over kappa. Okay, the best thing in order to explain this is maybe look at an example. But once more, roughly speaking, the osculating plane, okay, is the plane which locally at P contains as much as possible from all the planes which you can choose, as much as possible from the curve. Okay, and the osculating circle is the circle which describes locally around P the curve best from all the circles you can choose. Okay, so the osculating circle is a pretty good approximation locally of the curve. So maybe let's look at an example. Okay, so let's look once more at this example. At y is equal to x squared, because this is most easiest to understand. Okay, so a vector function describing it. We interpret it, this is a plane curve. The graph is a plane curve, but we interpret it as a space curve. So we have here x I plus, maybe I write here t square j plus 0k, 0 times k. Okay, so we first want to find the unit tangent vector. So the unit tangent vector is, okay, we take the derivative I plus 2tj, and for the second, so we first have to normalize it. So we see that the length of the derivative is equal to the square root of 1 plus 4t squared. So you see that the unit tangent vector is equal to Okay, so 1 over the square root of 1 plus 4t square I plus 2t over the square root 1 plus 4t square j. Now, if I want to find the unit normal vector, I have to take the derivative once more of this one. Okay, so I take the derivative of this one. Of course, this is now getting more messy. Okay, so we have here minus 1/2, 1 over, and then 1 plus 4t square to the 3/2, and we have from the inner derivative at I plus, and we have here, so for the derivative here we have the same, so we have minus 1/2, and then we have, but we have also 2t here, so we have 16t square over 1 plus 4t square to the 3/2 plus, so this was the derivative of this function, now the derivative of this one, 2 over square root of 1 plus 4t square. And then I have to normalize it. Okay, then I get the normal vector. So the normal vector would be this here, normalized. Okay, so I'm not going to do this. Okay, I'm just doing it for one point. So you see that our original curve is this one. And our third axis, okay, points in this direction here. Okay, so this, because we interpret this the graph of this function as a space curve. Okay, so if we look at this point here, the point x is equal to 0, which corresponds here to the parameter t is equal to 0. Okay, you see that the unit tangent vector, of course, is 0, 1. Okay, so points in this direction here. So this will be the unit tangent vector. You see that if you look at the derivative, okay, you plug in t is equal to 0, so this will be equal to 0, and this will be equal to 2. So you have the vector 0, 2. You normalize it, you will get the vector 0, 1. Okay, so this vector is this one. So this will be the normal vector. Okay. Now, the osculating plane, what is the osculating plane? It contains the point P and both of these vectors. So the osculating plane for this example is the xy plane. And this makes sense because I said the osculating plane is the plane which contains the largest part of which contains from the curve as much as possible. This certainly for this example is the xy plane. Okay, because the xy plane contains everything, the whole curve. Okay. So the osculating plane is the xy plane. Okay. And the osculating circle, so the osculating circle is in the osculating plane, so in the xy plane. Okay. For this point now, so the osculating circle here for this point is in the xy plane. Then you see this would not be enough to say is it on this side of the point or this side. Okay, so it's on the side where the normal vector points. So here, okay, it shares this point with the curve. Okay, and the radius is given by 1 over the curvature in this point here. Okay, which is 1/2. We just saw it before. Now, if you plot the osculating circle, okay, so the osculating circle is something like this circle here. And here you understand better what is the meaning of the osculating circle. The osculating circle is from all the circles you can place here. This is maybe I didn't draw it very well, but from all the circles you can place here, which contain locally some part of the curve. Okay. This circle will contain the largest possible part. Okay, so the osculating circle is a very good approximation locally for the curve. That's why the osculating circle is important. Of course, the tangent here, okay, would also be approximation, okay, locally approximation for the curve. But you see the tangent is not very good here, okay? Because the tangent is the x line. And the approximation is not very good. The osculating circle, okay, approximates locally the function much better than the tangent. But it's quite clear because the tangent is something linear and the oscillating circle is something quadratic. So you can normally approximate, get a better approximation by looking at the higher order, in some sense higher order approximation. Okay, so any questions to this? The direction of n you already get from this computation, because n has already a direction, namely the direction of the derivative of the unit vector. Okay, so you see that because I'm interested in the point t is equal to 0. You see, if I plug this in here, I get here 0, and here I get 2. Okay, and I have to normalize it, so I get a vector 0, 1, which already gives this vector. So the direction from this definition, I haven't proved that this if I use this this vector, okay, I haven't proved that the plane then, which contains t and n, okay, approximates the curve, contains the largest part of the curve. I haven't proved this. It's something you have to prove. So normally, what you just by doing formally these computations, okay, without having this picture, for n you always get the direction, okay, in which the curve is curved. But not only this, because you're in the space, okay. So it could also look like it's not necessary. The curve is not necessarily in the plane, okay. You always get for t and n, okay. If you look at the plane which is spanned by those two, t and n, this plane will always locally contain the largest part of the curve. I haven't proved this. This is something which must be proved, of course, but I haven't done this. But this is kind of the reason why we do something like this is because the convenient thing is you can completely forget about the geometric picture, okay, and you can just everything is possible to compute. You get approximations of the original function. You get planes which contain as much as possible from the original function, and so on. Everything is from the picture. Everything is removed, and you can just do computations. This area which I mentioned, differential geometry, is doing something like this. So what we want to do is what mathematicians have done in maybe 200 or 300 years was you almost completely we almost completely got rid of the picture. Okay, so everything can then just be done by computations, and you do not have to plot any picture anymore to understand curves. This is one of the aims. Okay, understanding curves without drawing a picture, and understanding the major properties of the curves, like how curved is the curve and so on. Now, the curvature is also something which is encountered in physics. This is what I want to discuss next. So, of course, you can use this, what I have discussed so far, vector functions, space curves, in order to describe motion in the space. Okay, so then you just interpret your vector function as the position of some particle at time t. Okay, so position at time t of some particle. Okay. Now, if you want to understand the velocity, okay, from a physical point of view, okay, what you are going to do is, okay, you will compute this here. This will describe roughly the average velocity, but it has also as a vector. If you take the limit, then you will get the velocity. So you will define the velocity at the point 0 as the limit t tends to t0. Sorry, h tends to 0. And this should be t here. Okay, which corresponds to our derivative. So this is also by definition how we define the derivative. Now you see that now normally the length of this vector, okay, is the speed. So the speed is the length of this vector here. Okay, which is the length of. And you see this makes sense because we saw already that that we can express this as the derivative of the arc length. Okay, so this is the amount of way you have traveled. Okay, so this makes sense here to define the speed as the absolute value of the derivative. And you can also define the acceleration, which is now directed and which is nothing else but the derivative of the velocity function, or the second derivative of the original position function. And you see here, this kind of this way of writing things, this notation is very convenient because if I give you, for instance, if I give you the acceleration function, I give you the velocity at a certain point, and I give you the position at a certain point. Okay, you can use this and the integral we have defined formally to go back and compute the position function. Okay, so you see here why the integral, why we have considered the integral. Okay, it's a convenient notation here. Okay, to write things, and it just satisfies the same properties as the integral we have defined last semester. Now, I just want to show you that the velocity function here, so this vector function, one of the questions, of course, is where is this vector function? And you will see in a minute that this is related to what I have discussed just 5 minutes before, namely osculating planes and osculating circles and curvatures. Okay, so if we look at the if we look at the velocity, so the length of the velocity, as I said, is the speed, and the direction of the velocity is what we called before the unit vector. Okay, the unit tangent vector. Now, the acceleration is the derivative of the velocity. Okay, so I can use this here. So, and I use the. You have to notice both of them depends on the time. So I use the rules which we have already proved. So this is this here times the unit tangent vector plus v times the derivative of the unit tangent vector. But if you look at the unit tangent vector, we saw that if we look once more at the definition of the curvature, or the formula which we got is this is the length of the derivative of the unit tangent vector over the length of the derivative of the vector function. But this here is once more the v, because here we are talking about motion in space, and this what we have here is the speed. Okay, so this is the length here of t times, and here we have the speed. Okay, so you can write this as the derivative of v times the unit tangent vector plus, okay, and here you can replace this by the unit vector, by the vector which has the same direction but length 1, but this was by our definition the normal vector, okay, and then you have to multiply it with its length, but the length is equal to kappa times v. Okay, so you have it here. You have kappa times v squared times the normal vector. Okay, so you see that acceleration, because as I have explained before, the osculating plane, okay, is spanned by those two vectors. Okay, so you see that the acceleration always lies in the osculating plane. Okay, and it has two components. One component in direction. So if I maybe make a plot. So this is the motion performed by some particle. So this is the trajectory which is traced out by some vector function. And we have now, for some point, okay, we have here the unit tangent vector and the unit normal vector. We see that the acceleration, okay, lies in the osculating plane, and it has two components. One component in direction of the movement, okay, of the motion. This is the direction of the motion of the motion, and one component which is perpendicular to this direction. Okay, and you see that this component which is perpendicular to the motion, okay, depends. The length here, okay, depends on the curvature, and of course this makes sense because you know that by Newton's second law of motion, the acceleration and the force are proportional. Okay, so you see that here if the curve is very curved, okay, then the force you will feel here, okay, will be very large, okay, which is clear because if the curve is more curved, okay, and you drive around the corner, okay, then you will feel the force which is pushing you to the window. So the component, okay, which is perpendicular to the direction of motion, of course perpendicular in the sense that we are in the osculating plane, okay, depends on the curvature. Okay, it kind of makes sense. But from here you see that that acceleration always lies in the osculating plane, and it has those two components here. Also in our textbook you see you find two formulas how you can easily compute from the given position function of a particle those two components. I'm not going to discuss this. It's just interesting to mention that this is related to what I have talked before. Now, the last thing which you find in our textbook, actually in this section, actually you'll find here many applications of the results we have discussed before. You know this already from physics. I guess that's the notation we have introduced and the laws are very convenient in order to discuss motion in the space. But something which is in particular striking and which our textbook discusses is you can use this kind of notation and the rules we have, or the differentiation rules we have discussed so far in order to give a proof of Kepler's laws of planetary motion. And this is something which is quite interesting and clearly demonstrates the convenience of introducing differentiation and integration for vector functions. So I'm not sure whether I have 20 minutes maybe are enough. Okay, so what I want to show is, and this is, you can also find this in our textbook. You know the three famous Kepler's law of planetary motion. The first one tells you that the Earth is revolving around the Sun in an elliptic orbit where the Sun is in one of the focus. So this is the first one. That's essentially the one which I want to concentrate on. Okay, so if you have here the Sun, then Kepler observed that if this is the Earth here, that the Earth is revolving around the Sun in an elliptic orbit where the Sun is in one of the two focus. Okay, so this is the first law of planetary motion, which was discovered by Kepler. You also know the second one tells you if you connect the Sun with the Earth and you look at the area which is swept out, okay, by this half line, then in the same time the same area is swept out. And the third law tells you that the time it takes to get around once squared is proportional to the length of the major axis cubed. Okay, these are the three famous laws. And the striking aspect, which was discovered by Newton, because Newton more or less introduced calculus for vector functions, was that you can prove this very automatic without even looking at the sky. Okay, so for instance, if you would have been born in this room here, no windows, okay, still, if you are smart enough, still you can discover that our Earth, but maybe you do not know that we are on a. So you have also discovered that we are on a planet which has the shape of a ball and so on. But if you know this, then without even leaving this room, you can prove you are able to discover just using calculus that the Earth is revolving around the Sun in a elliptic orbit where the Sun is in one of the focus. If you know enough calculus, okay. So this is quite striking. So you do not have to look at the sky and do observations. Nothing. Now, the only thing, of course, you have to first you have to figure out certain laws of physics. And the only thing, and this is what Newton discovered, is you just need two basic laws, which you can, of course, find here without going outside. Namely, the first one is the second law of motion, which tells you that force and acceleration are proportional. Okay, and where this vector is given by the mass, this is the first thing. This is something you can find out here. You do not have to leave for this. And the second one is that the gravitational force between two objects, okay, satisfies the following law. So this is Newton's second law of motion, and this is for the gravitational force, okay, which is given by minus. Then you have here g, which is a constant, a gravitational constant. Then you have the mass of the two objects, okay, divided by their distance cubed, okay, and multiplied. Because this is a vector, so multiply. This is the direction between the two. Okay, so this is what is called the gravitation law. These are the two rules from physics, the two laws from physics you have to discover, and the rest is calculus. Okay, from those two you can prove very automatically just by doing computations that the Earth is revolving around the Sun in an elliptic orbit. Okay, actually, because if you never leave, of course, maybe you can prove that the Earth, that the trajectory of the Earth is either an ellipse or a hyperbola or a parabola. Okay, so which means you can prove even more. You can prove that only those three. For planets, you have only those three possible trajectories. Okay, so now let's discuss how to do this. So you will see that the rest is really automatic, okay, just doing computations. So the first thing we will do is we have to fix a coordinate system. We have to fix the origin of our coordinate system. And what we place in the origin is the Sun. Okay, so the Sun will be the origin of our coordinate system. Also, we neglect all other gravitational forces. So only the Sun is the main source for the force. Okay. Of course, you have in reality you have more of them. Okay, but the Sun is much larger than the other, for instance, other planets, so that you can neglect the force which comes from the other planets. okay, or other objects in the space. So we will place the sun in the origin of the coordinate system. So you have then something like, okay, here's the sun, and here's the Earth, and this here is then the trajectory which you get, which describes the movement of the Earth around the sun. Now, the first thing, so you see that here what you have is the velocity. The first thing what we do is we look at the derivative of the cross product between the, maybe I should always indicate the time, because some quantities will depend on the time, some not. So we look at the derivative of the cross product between the trajectory and the velocity. So here we know that, okay, we can use the product rule. So this is equal to the derivative of this one times, okay, we leave this unchanged, plus, and then we leave this unchanged times the derivative of this one. But you see that so you can write this as because this becomes the velocity, so you have the cross product between the velocity and itself plus, and this here becomes the acceleration. Okay, but the cross product of a vector with itself is 0, and you see that the acceleration is given here by this law here, and this law also here you have also r of t. Okay, so this will be 0 as well. So both of them are 0. So what you get is 0. So the derivative is equal to 0, which means that this here must be a constant, independent, a vector which is independent of t. Okay, so you see that the cross product between r of t and v of t is equal to a vector h, which is a constant. So this is a constant vector. Okay, and this already proves, this already rules out many possibilities for the orbit. Okay, because you see that this already shows you that the orbit must be contained in a plane. Okay, so from here you know, for instance, the Earth cannot go around like this here. Okay, because you see, because of this here. So we already have obtained that the orbit must be inside a plane. Okay. Now, in order to go on, what we do next is actually I introduce the corresponding unit vector to this vector, which I denote by u of t. So u of t is equal to r of t over the length of r of t. And for this one, I wrote r, if you look at the way I wrote the gravitational law before. So r of t is this length here. Okay, so we can write h is equal to, now we want to express everything in terms of u of t, so we can write here r times, and for this one we can write u of t times, and for this one, so actually what we also know is that the force, because the force is given by minus g m over r to the cube, but I can write here now r square, and I get here u of t. And because of Euler's second law of motion, so this must be equal to m. So what is u of t? M times a of t. Okay. Actually, I do not need this yet, but this is the derivative of this vector here. So I have here once more r times. Actually, I'm not sure whether I should really write always t, because sometimes the vector does not depend on t. Sometimes it does. but most of the time it depends on t. Okay, let's write every time. So here we have also r of t times u of t, but the derivative. Okay. So here we can use again the product rule. So what we get is r of t times u of t times, and you see that here, okay, by the product rule we have the derivative of r of t times this unchanged plus r of t times, and here we have the derivative of u of t. And here we can, because of the cross product, okay, we can multiply this with this term plus multiply this with this term here. Okay, so this becomes then, you see, if I multiply this here with this term, because I have the cross product of u with itself, this will be equal to 0. And if I multiply this here with this one, so this one I must keep. So I have here r square times, and then the cross product of u with the derivative of u. Okay. Now, what I want to look at next is the acceleration times cross product with this vector h here. Okay, so for this vector h, we have already this expression here, and for a of t, we can use this here. So we can plug in this. So we have for a of t, we have minus gm m over r square u of t, and then the cross product with this here. So r square I should make a bracket, u of t cross product with the derivative of u of t. So you see that this becomes sorry, the m goes, so I can drop the m here because of this. Okay, so I can take out the constant. So what I get is minus gm. This is the constant. And then what I have left is the cross product of u of t with the cross product of u of t and the derivative of u of t. Now, for this one, we had last time, I have shown you I have shown you a funny rule for this one. So here we have minus gm, and then you can rewrite this. So you have three vectors and always the cross product to u times the derivative of u, and so this is a scalar product with u minus u times u, and then scalar product with the derivative of u. But you see that because u is a unit vector. Now, sorry, for all of them I have to give it a t. Here's a t, 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 here's a t. But this here is a vector function of length 1. So the derivative will be orthogonal to this one. So this will be equal to 0. And here you see this is just 1 because this is a vector function of length 1. So what I get is g m u of t derivative. So this is already pretty easy expression. So you see that the cross product of a of t with h does not depend on t, must be equal to this one. Now, why is this helpful? You see, I can rewrite this here. This is the derivative of the velocity times h. because this does not depend on t. Okay, so if I use the product rule here, it's the derivative of this one, this unchanged, plus this unchanged derivative of this one is 0. Okay, so this here will be equal to and this will be equal to this one, but this one I can write as gm u of t derivative. Okay, so those two vector functions have the same derivative, so they just differ by constant. Okay, so the cross product of the velocity function with this vector h is equal to gm u of t plus a constant, a vector, of course, which does not depend on t. Okay, and now I finally can, because I have just said that the sun is in the origin of the coordinate system. I haven't said how to choose the x-axis, the y-axis, and the z-axis. Okay, the z-axis I will choose in direction of h. Okay, and the x-axis I will choose. You see that if we once more look at, okay, so this is the sun and this is the earth. Okay, so the vector r of t is here. The vector v of t, not necessarily orthogonal, but here. You see that this vector here, okay, lies in the plane, okay, where the movement takes place, because this vector h is orthogonal to those two. Okay, so the cross product between them, those two, is in this plane here, which you see here, in the plane where the motion takes place. Okay, so this one is in a plane where the motion takes place, and this one as well, because this is just this one. So you see the c is in the plane where the motion takes place. Okay, if I choose this z-axis in direction of h, okay, then the motion takes place in the xy plane. Okay, and I choose the x-axis in direction of c. That's the way I choose the coordinate system. Okay, now actually we are almost there. Now from here we multiply everything, the dot product with r of t. Okay, so if you look at the dot product of r of t with the vector product of v of t and h, you remember this was called the scalar triple product. Okay, and for the scalar triple product, we have a formula which tells you this is equal to the vector product between r and v, scalar product with h. This is equal for the scalar triple product. Now this vector here, okay, this was by definition our h. So what we have here is h times h. So this is the length of h, which we call h without using this fat notation, square. Okay, so this h here is the length of h. Okay, so if I multiply everything with r of t, what I'm getting here on the left-hand side is h square. So what I have here is h square is equal to, now on the right-hand side, I get, okay, so the r, so g m, and then I have the dot product between r of t and u of t, plus, and then I have the dot product between c and r of t. Okay, now this here, the first part is because this one is the length of r multiplied the scalar product with the u of t, but u of t times u of t, the dot product is equal to 1. So this is just r of t plus, and for this one I can write, okay, so for the dot product we know this is the length of c times the length of this one, which is r of t, times the cosine of the angle between them, theta of t. Okay. Now from here I can, because what I'm interested in is r of t. Okay, that's what I'm interested in, because r of t describes the trajectory, so it describes the orbit of the planet. Okay, so if I use this, maybe for this one we introduce c, okay, as the notation. So you see that what we get here is h squared over, and then we have gm plus c plus cosine of theta of t. So we take out the gm, then we have 1 plus, and here we have c over gm, and here we have a cosine of theta of t. Okay, and this here we call E. Okay, now the rest is just, I'm almost finished, so just give me 2 more minutes. So now I can write everything as h squared over gm over, and here I have 1 plus E and the cosine of theta of t. Okay, and now what I want to do is, okay, I want to have E here as well. So I have here E times, and the rest is what? H squared over C over 1 plus E cosine of theta of t. And this here I call D. Okay, so what I end up with is ED over 1 plus E cosine of theta of t. And now I have just to, I'm not sure whether you have learned this in high school, but if you have a conic section, okay, a conic section is either a hyperbola or a parabola or a ellipse. Okay, if you have a conic section, normally in high school, I guess you define the conic section by giving a focus and you're giving a line, okay, and you define. I guess this is standard notation, and then you define the conic section as all the points which have where the ratio of the distance to the focus and to the line is constant. This is normally the definition, I suppose. You find it also in our textbook. So normally you define conic sections like this, and then you can easily show that from this definition you easily see that the parametrization, a conic section in polar coordinates is given by this here, where E is the so-called eccentricity, and D is a constant which is given from the major axis in the case of the ellipse. So this means that here the parametrization is different of the ellipse. So you use the focus as the coordinate, as the origin of the coordinate system. So you place the original of the coordinate system into the focus, and you use polar coordinates for a point. So here you have the theta, and here you have the r. And if you parameterize an ellipse like this, then the equation which you get is this one. Okay, and but not only for the you get the same equation for the hyperbola and for the parabola. So this equation, okay, must be a conic section. So this means that for the orbit, that's just 3 choices left: a parabola, hyperbola, or a ellipse. And since for the Earth must be closed, okay, for this you have to go outside, okay, to observe that the orbit must be closed. Okay, it must be an ellipse, because the ellipse is the only conic section which is closed. But this is not the main thing. The main thing you see that starting from the second law of Newton's second law of motion and the gravitational law, the rest is very automatic, just calculus. Okay, I can just do computations, and at the end I can prove that we revolve around the sun in an elliptic orbit. And you can use similar tools, not very different from this, in order to prove also the second and the third law of motion. This is, I think there is an exercise in our textbook which guides you through a proof for the second and the third law of planetary motion.